Good day, I'm Norman Wildberger. Today we're going to start with abstract algebra, and we're going to introduce the simplest kinds of objects that are broadly used in undergraduate mathematics, which are linear spaces or vector spaces. But our approach to these will be a little bit different because we're motivated by our data structure point of view. So our strategy is to base things on these very familiar arenas that we've had lots of experience with: the natural numbers, the integers, and the rational numbers. And in particular, we're going to consider today the simplest operation only, which is addition. So we want to generalize what's happening with these very simple kinds of arenas with just the simplest operation. So let's remind ourselves that when we take 2 plus 3 equals 5, what's really happening there is we have an mset. 2 is really the mset consisting of a couple of marks, and there's the mset consisting of 3 marks, and we're really adding these msets. And when we take the difference, say 3 minus 4 equals minus 1 in this arena here, we are also doing something that's pretty well mset addition. This is really the same as 3 plus minus 4 equals minus 1. And we can look at it from an mset point of view by taking this mset here, which is 3, and here's the mset minus 4, which consists of these anti-marks, 4 of them. And when we add these two things, we get the mset consisting of a single anti-mark, which is minus 1. So in all of these cases, the addition, the basic operation, is really addition of msets. And that's going to be the key point that we're going to structure our initial abstract algebraic objects on. Msets are not that familiar kinds of data structures for most undergraduate mathematics these days. And so maybe we don't really appreciate just how flexible and useful they are as a tool for building up abstract algebra. But a key property, all right, a key point is that we can always add msets. Here's an mset, no matter what it contains, and here's another mset, no matter what it contains. We can always add those msets, just dump out the 2 boxes into another box. And we don't need to have 2 of them. We can have 3 or 4 or more of them. We can have lots of containers. We can just add them all together to get one big cumulative container. So it's a very easy conceptual kind of operation that's really underlying what we're doing here. Okay, so suppose that A, B, and C are msets from some given context. Okay, so we have some specific context. We have legitimate msets coming from that context. Let's call them A, B, and C. It's actually not that important that there's 3 of them. I just want to employ 3 of them rather than the usual 2 to get you used to the idea that this is not really a binary situation predominantly. Okay, so we have these msets A, B, and C. What can we do with them? Well, we can always add them together in various ways. We can take A plus B. We can take 2A, which is just the same as A plus A. We can take A plus B plus C. We can take a more sophisticated combination like 2A plus 3B, or maybe even 5A plus 2B plus 7C. All of these are just direct, obvious generalizations of dumping things out into a bigger box. Okay, so motivated by this, let's say that if A, B, and C are msets, then any mset of the form Ka plus Lb plus Mc, where K, L, and M are natural numbers, any such mset is a linear combination of A, B, and C. So we'll introduce this idea of a linear combination of msets. This is a basic kind of vector terminology, but we're not really working in a vector situation with geometrical vectors here. We're just working in this much broader context of just having msets. We're talking about taking linear combinations of msets. Now this slide here reinforces the idea that we do not necessarily have to restrict ourselves to a binary operation. We're considering the addition of msets in a more general way. So for example, if we have msets A, B, C, and D, and they have various elements, we can add all 4 of them together at once. So here, for example, we're dumping out the contents of A, which might be something called K, and another thing called X, and something else called L, and 2 things called Y. There's B we're dumping out, there's an X, a Z, a Z. C we're getting X and Z. D, out comes X, Y, and W. So all these things are just being dumped out, and there's no need therefore for us to fuss around about brackets. We can just write A plus B plus C plus D intrinsically, fundamentally. And if we want to write down what that mset is, well, we just collect all these various things. K, X, L, Y, Y, X, Z, X, Z, Z, X, Y, W in no particular order, and that's the cumulative sum. So it's a little bit of a different kind of orientation, because usually in abstract algebra we concentrate on binary operations. But here the mset point of view really gives us a broader picture. Okay, so now let's introduce the idea of the span of some multisets. So if A, B, and C are multisets, and so is M, and these are from some context. So we're assuming that we have some given context in which we've generated some meaningful msets. We don't have a general definition of what an mset is. We build up the notion of msets step by step, little by little, and we create more and more complicated msets. So what we're just proposing here is that we have some prior arena in which we have defined, well-defined objects which are msets of stuff. Okay, and here they are. We've got M, A, B, and C. We are now going to define the following thing. We're going to say that M is in the span of A, B, and C, precisely when M is a linear combination of A, B, and C, in the sense that we've just described. So M being a linear combination of A, B, and C, that's exactly what we mean when we say that M is in the span of A, B, and C. And note that I've put A, B, and C sort of together in fact, an mset. So I've created a bigger container that contains the A, B, and C, which are the ingredients of the linear combinations we're considering. So for example, if A is the mset 1, 2, 2, that's an mset of numbers, in fact natural numbers, and B is the mset 1, 3, then this one here, 1, 1, 1, 2, 2, 3, 3, that's an mset. That is in the span of A and B. Why is that? Well, the claim is that this is a linear combination of A and B. And can we see what it is? We're going to have two of these and one of these. So this thing here is in fact A plus 2B. We can write it as a linear combination of these given msets. And this one here, 2, 2, 2, 2, 1, 3, 1, 1, is also in the span of AB. Let's see if we can check that. So how are we going to write this as a combination of these two? Well, I guess we're going to need two of these because we have 4 2's here and 2 2's here and no 2's here. So we'll take 2 of these and one of those. That'll generate the 1, 3 there, and 2 of these gives us 4 2's and 2 1's. So this thing here is 2A plus B. This one was A plus 2B. This is 2A plus B. Both of them are in the span of AB. So here's a practical kind of example of this in real life. Suppose we ask what amounts of money can be expressed using only 10-cent and 25-cent coins or pieces. Well, so any such amount in cents must be a multiple of 5, because these are both multiples of 5. So anything that we get as a sum of these various things will have to be a multiple of 5. But not all multiples of 5 can be obtained. Obviously, for example, 5 itself cannot be obtained using just a collection of 10 and 25-cent pieces. So the ones that can be obtained are, well, first of all, 0. 10 cents is of course included, and 20 cents as well, because that's just 2 of those, and 25. But notice that 5 and 15 are missing here. 30, and then 35, and then 40, and then 45, and 15, 55. In fact, it's not too hard to see that after this point here, we can get any multiple of 5 by just using 10 cent and 25-cent pieces. So all positive multiples except for 5 and 15 are obtainable this way. So in a multiset language, what we're doing is we're talking really about the span of 10 and 25, where we're thinking as having 10 and 25 being msets, which of course they are because natural numbers are msets. So taking linear combinations of these things fits inside the discussion that we've had so far. So for example, 35 is an element of span 10, 25 because it can be written as one of these plus one of those. All right, now let's have a look at a little bit of a richer situation in 2 dimensions. So we're going to look at some 2-dimensional spans. So here is our usual xy plane, but we've labeled it x1 and x2. Okay. And let's start with these 2 vectors, E and F, where E is the usual standard basis vector 1, 0, and F is the standard basis vector 0, 1. Now this traditional notation for a vector can be sort of translated into our somewhat more modern or novel framework by thinking of it as perhaps this row freeze here, 0, 1, 0. We're really supposing that we're starting our indices here with 1 and 2 because the axes are labeled x1 and x2, and so we're agreeing that there's no 0 component in this situation. So there's the vector E and there's the vector F, either as vectors or as sort of really vexels. Okay, so what would the span of EF be then? The span of EF is just those vexels that we can obtain by taking linear combinations of these ones. So, in fact, what we end up getting is just this green lattice here, this lattice, kind of a square lattice that occupies a quarter of the plane, sort of 1 quadrant, because we're only allowed to take positive combinations of the 2 vectors. That's the critical thing. So any vector like that one there could be obtained by a certain number of E's and a certain number of F's. More interesting, perhaps, is if we choose some more random kind of vectors. So let's consider V equals 3, 1, which is that vector there, and U, which is 1, 2, which is that vector there. In our freeze notation, this would be written this way, this would be written this way. Now, span of UV, which refers to linear combinations, positive linear combinations of U and V, has a nice geometrical shape like this. So there would be V, there's 2V, there's U, there's 2U, here's U plus V, this one would be V plus U, so 2 V's plus a U would be this one here, and we could do that algebraically. 2V plus U would be 6 plus 1, that'd be 7, and 2 times this plus this would be 4. So this is the vector 7, 4. So the span of EF is this green lattice, and the span of UV is this blue lattice. In some sense, they look quite the same algebraically. I hope you can see that there's some kind of similarity between the 2 of them, even though they physically look different. Now I have to remind you that when we're adding vectors from our point of view, vectors are really just vexels, and vexels are just multisets of singletons. So the addition of vectors component-wise is really just a reflection of the more fundamental multiset addition of the underlying vexels. All right? So we really are working in the context of adding multisets here when we're talking about these kinds of vectors. Okay, so now let's increase the subtlety by throwing in a third vector. So we had V equals 3, 1 and U equals 1, 2, and now let's consider a third vector, W, which is 2, 2. So I've zoomed out a little bit here to give you a bigger picture. There is the vector V, which is 3, 1. There's the vector U, which is 1, 2, and now we have this vector W, which is 2, 2 as well. Now in blue here, you can see the former span of just U and V. Just all possible combinations of U and V, at least that we can see. Of course, it extends upwards there. But now we want to consider the span of v, u, and w, the span of all three vectors, which means we're allowing ourselves combinations, linear combinations of all three vectors. So for example, not only do we have w, but we also have w plus v, w plus 2v, and w plus 2v plus u, w plus 2v plus 2u, w plus 2v plus 3u, w plus 2v plus 4u, etc. So I've now added in these sort of empty circles, these are now the additional vectors that are augmenting the VU span when we throw in the W as well. Now if we stare at this for a little while, you can see that what happens seemingly is that as we go further up in this direction, then we start getting pretty well most points or most vectors there that are on our basic integral lattice. But down here, when we're sort of starting out, we're not getting every such vector. We're only getting some of them, and it's a little bit haphazard. So describing something like this precisely, it's not impossible, but it's certainly much more complicated than it was when we just had two vectors, u and v. So what we've really kind of done is we've taken an mset of msets. We haven't said it this way, but that's sort of what we're doing. We're taking a bunch of msets to start off with. But a bunch of msets is really like an mset of msets. Because in principle, we're not excluding the possibility that there might be some repetitions amongst the msets that we're starting with. So let me represent that by this example. So here we have M, which is an mset consisting of the msets A, B, and C. So we have an mset of msets. And now span of M, that is the msets which are linear combinations of A, B, and C. So before I wrote span and then brackets A, B, and C, but now we can just write span of M, because M is the mset which is containing A, B, and C. So we can regard span of M now as something like a type. Okay? It's describing certain msets which are linear combinations of A, B, and C. So it's a little bit like a type, but we prefer perhaps to use the term space. So we might like to talk about the space span of M. So we're going to regard this term as a meta-mathematical notion at this point. So we're not going to define precisely what space means, just as we haven't really defined precisely what a type is. We've just been using this a little bit informally, and we're going to do the same kind of thing for space. Okay. But it's a useful kind of terminology, I think, and it connects with the usual terminology in linear algebra. Okay, so we've actually been quite naive. All what we've done is we've just taken some msets, put them in a box, so called that an mset of msets, and then we're considering the span of that box, which is linear combinations of the msets that we've chosen. So this is a very simple-minded kind of way of creating an algebraic structure, but it already has most of the properties of what's called a vector space or a linear space in modern linear algebra. Namely, let's describe it this way. So we'll suppose that we have span of M. M is some mset of msets. Like perhaps you can think of M as the mset consisting of A, B, and C, where A, B, and C are msets. So we're going to take U, V, and W in this span. So each of these is a linear combination of the elements of M. And let's take N and M to be natural numbers. Now here are properties of the arithmetic of these linear combinations. And they're really all very familiar to us because we're just iterating things that we already know about the way we add msets. So U plus V plus W equals U plus V plus W. This basic associativity which is really just saying that the order doesn't matter. We've emphasized this already. It's not really a binary operation, so it doesn't depend on what order we put things in. U plus V equals V plus U. Yes, it's commutative because there's no order when we empty boxes into a bigger box. 0 plus V equals V. Okay, that's interesting. So the 0 here refers to our particular M set, the empty M set. That's what 0 is. 0 is the empty M set. And we're saying that if we take the empty M set and add another M set, well, then we get the other M set. And we know that that's true. These properties have to do with multiplying an M set by a natural number. So if we have U and V in our M sets, and we take their sum and then we multiply by n, like 2 or 3, then we get NU plus NV. On the other hand, if we take the sum of two numbers, n plus m, and multiply u by that sum, that's the same as n times u plus m times u. So we have two kind of distributive properties, one with respect to the M sets and one with respect to the natural numbers. And then there's another kind of sort of multiplicative law with respect to multiplying by numbers, namely that if we take M set u and we multiply it by the number m and then we multiply that by the number n, the result is the same as taking u and just multiplying it by the number nm. And finally, if we take an M set u and we multiply it by the number 1, then we just get the set back again. Okay, so these are pretty well the usual ingredients of the definition of a vector space. So when you study linear algebra and you eventually get to defining a linear space or a vector space, these are amongst the properties. In fact, they're almost all of the properties. There's essentially only one other property that we don't have, and that distinguishes what we've done today from what we're going to do next time, which is sort of linear spaces proper. This is just a preliminary to that because we don't have integers floating around, or more particularly, we don't have rational numbers. So far, our numbers are just natural numbers. We're only allowing ourselves to multiply M sets by 2 or 3 or 5 or 1 or 0, but not by -1 or -7 or 4/3. Okay, that's really the only distinction between what we have here and the linear algebra that's really the studied in undergraduate mathematics. But it's important to realize that what we do have is really just M set arithmetic. We haven't really gone past or beyond things which are very familiar to us. We're just doing basic M set arithmetic. So in our next video we want to go further, and we really want this -1. Okay, the -1 allows us to subtract as well as add, and that's going to have an important technical effect, that it's going to eliminate the kind of strange behavior that we saw when we looked at the span of those three vectors in the planar situation, where you had sort of uniformity up in this area, but the bottom of it was rather sporadic and unpredictable. Okay, so when we go from natural numbers to integers as coefficients of our linear combinations, then things become much simpler and more manageable, sort of conceptually or theoretically. So there's big advantages that we'll see next time. I hope you'll join me for that. I'm Wildberger. Thanks for listening.